I will talk about some things we can do with ions, so they can be used for analyzing and for modifying materials. Of course, this is not possible in one webinar to tell everything, but I will try to give you some glimpse so you can have idea what you can do. So just introduction, I'm coming from the Ion Beam laboratory. This is the Ruđer Bošković Institute Accelerator Facility. So we run two accelerators, 1 megavolt Tandetron and 6 megavolt Ion tandem. And we can accelerate different kind of ions from protons to gold ions and cover wide range of energies. So from 200 keV up to 30 MeV ions. So ions, when they are produced in the ion source, they have to travel through the vacuum tubes, and there are some optical elements which bring them in the scattering chambers, where we can do different kind of experiments. So here you can see that we have one nice feature that we can deliver in two beam chambers ions from two accelerators simultaneously. These are our newest beamlines for irradiation of fusion materials, this DIFU beamline, and dummy for this is the dual microbeam setup. So as Mary already said, this is the webinar in the framework remade at ARI project, and Ruđer Bošković Institute Accelerator Facility is part of Radiate Consortium, which consists of many partners. This is actually a group of accelerator beam facilities around Europe. If you want to find more about the different abilities of partners, you can visit the project website and find something about consortium members. So if you visit the website, you will see there is a catalog of techniques, and those related with ion beams are placed in these 4 folders. So you have ion beam analysis spectrometry, ion beam composition mapping and imaging, focused ion beams, and ion beam material modification. And my colleague, Johan Mershout from IBIC Belgium, gave seminar about introduction to ion beam analysis, this first box, which is related to spectrometry, and he gave you introduction about RBS, Rutherford scattering and ion channeling, elastic recoil detection analysis, NRA nuclear reaction analysis, particle-induced X-ray emission, and proton elastic scattering analysis. So if you want to see Johan's webinar one more time, you can visit also, it's recorded, and you can visit YouTube channel and see the webinar again. So I will talk about other 3 boxes today. I will mention these techniques, PIXE, PIGE, but in context of mapping and imaging. And also we'll talk about these 2 techniques Johan didn't talk about at all. One is Scanning Transmission Ion Microscopy, and the other one is Ion Beam Induced Charge, which is a really nice technique for measuring electron transport properties of semiconductor materials and devices. Also, I will talk about techniques mentioned in the other 2 boxes, which is ion beam materials modification and focused ion beam. So what we can do with this, so we can modify materials, so we can do some doping in materials, we can do single implantation for quantum technology applications, we can do defect engineering in oxide semiconductors, 2D materials. We can test radiation detectors for radiation hardness. We can directly write into material, and we can do ion beam lithography. So some of the techniques are done with low energy ions. This is the range from a few keV to a few hundreds of keV, like focused ion beam, FIP, helium ion microscope, or ion implanter. And for some techniques, we can do some material modification also with ion accelerator in using ions in the MEV ion range. So just a brief couple of words about proton-induced X-ray emission or particle-induced X-ray emission. So we ionize inner shells of atoms, which are filled in a very short time with electrons from outer shells. And for energy conservation, one X-ray should be emitted. And actually, as we have in every atom very defined shells where electrons move as in inner shells, we have with this emitted X-ray signature of element. So we know which element is present in the sample. Usually we use 2 to 3 MeV protons to do PIXE. And we can analyze elements from sodium to uranium. You can analyze even lighter elements, but the detectors get more complicated because of the interface between detector and vacuum. PIXE is very nice because it's multi-elemental, requires really small sample, can be done in air and in vacuum, and is non-destructive. And the high sensitivity can be obtained for elements in the for Z range from 20 to 40, and for heavy elements, and the sensitivity for those elements is in the ppm range. So here you can see one spectra of aerosols on nucleopore filter, and you can see nicely that you can detect many elements. This particular detector is optimized for elements from calcium up. There is also another which is not shown here to cover lighter elements. PIXE is not optimum technique and good technique for depth profiling. And the problem is that you can't get information about organic components. Therefore, you can use other techniques like ERDA or also RBS technique to get information about lighter elements in your sample. The other technique is proton-induced gamma ray emission, or PIGE. This is actually happening where energy of your ion, your proton, is sufficient to overcome the Coulomb barrier, and you have nuclear reaction. So PIGE is a part of nuclear reaction analysis. We have nuclear reactions and elements which we can analyze very nicely. Particular isotopes are like lithium-7, fluorine-19, sodium-23, magnesium-24, aluminum-27, silicon-28, potassium-31, and also with some other neutron and alpha-based reaction. I mean, proton PN or P alpha, we can also analyze the boron-10, aluminium-27, and lithium-7. And here is the example of one PIGE spectra. This is a spectra of lithium ore. And to get this spectra, my colleagues use protons with energy of 3.47 MeV. And you can see that you can nicely see a fluorine, determine fluorine, lithium, magnesium, aluminum, and silicon in such a spectra. And as we can measure aluminum and silicon with PIXE, and in most cases also magnesium, then this information is really unique because you can't get it with PIXE, information about fluorine and lithium. So to get imaging, you have to design instruments or use instruments which are called ion microprobes. And these are basically instruments that focus, they use lenses to focus proton beam to micron dimensions at the sample. Usually you use 2 to 3 MeV protons and you focus them to micron dimensions. Then you need to have a scan generator, which will scan your beam along the surface of the sample. And what you can get 2D images with distribution, 2D distribution of elements. So you get elemental maps for different elements. You can then correlate elements, so you can see how they are correlated among themselves. Here is one nice example. Of course, you can, when you have beams, you can put many detectors, and you can do several techniques at the same time. Here is a very nice example of simultaneous use of PIXE and PIGE for the analysis of batteries. So to get information about zirconium and cobalt, you have to use PIXE. And to get information about lithium, you have to use PIGE. So those techniques can be used simultaneously. And you can get specific these 2D elemental maps and see what is going with the battery. In this case, this L at Z base cell was charged to 4.2 volts, so it was some working conditions. So you can put it in different working conditions and see how the elements are distributed inside this cell. Sometimes you can build special cells to also to study this in operandi behavior of your batteries. All this can be done with a microprobe. One technique which is also very interesting and used to analyze thin samples is scanning ion transmission microscopy, or scanning transmission ion microscopy, so-called STIM. And basically is based on the idea that ions pass through the sample. So the sample should be thin enough so that some energy of the ion is left and that we can detect it in the detector, which is beyond the sample. This technique is very nice because it can give you some information about the thickness of your distribution of densities of your sample, if you know the thickness, or if you don't know the thickness and you have the same density, you can get distribution of the thicknesses. So here is a one density map of the insect wing, which was done with, in first case, with 2 MeV protons. And here in second case, this STIM was applied to the same sample on the different place, but with 6 MeV oxygen ions. So you immediately see that the better contrast is obtained with oxygen ions because heavier ions, they leave more energy per unit path, and you can get better contrast information if you use heavier ions in STIM. STIM is very often combined with microPIXE because with STIM, if we have a sample of let's say very thin biological sample, which is thick usually 2 to 5 microns, you can find the interesting spots on your sample by doing STIM imaging. So you can see where you have density variations, and you can then use this to do elemental mapping. So you can localize the place you want to analyze, and then you can do elemental mapping. Unfortunately, STIM and PIXE can't be done at the same time, but can be done one after another, because STIM is a low ion technique. So as we put particle detector beyond the sample, high currents, which we usually use for imaging with PIXE or with PIGE, will destroy the detector immediately. So therefore, we have to reduce the current to femtoamps, let's say currents about 1,000 ions per second, to do STIM imaging. When we find what we want to measure, then we can just increase the current, which means in our case, just open the slits at our microbeam, which is defining the current. And then we can do elemental imaging. Of course, as I said, you have different elements on the same area of the sample. So you can later correlate elements and see how they relate to each other. So this was the imaging of the cancer cells. So first was necessary to find the interesting region of the cancer cells, and then image. This is the big scan size. So this is a lot of them in some tissue. Second technique, which is also low current technique, because you use much lower currents than you use for PIXA and PIGE, is ion beam induced charge. And this is actually very, very nice technique. And we use it a lot in our lab for different things. It's an ideal radiation source to test charge collection efficiency of detectors, but also to test radiation hardness of detectors. So you can see how your detector is working, then you can put a load of ions on it and see what will happen with charge collection efficiency later on. So instead of the sample in scattering chamber, you put the detector at the sample position and you put it in the working condition. So you put your charge and preamplifier, and you can get the signal from the detector. So beauty is that we can use as many ions as we want, I mean different. So we can start with light ions, which is usually used for IBIC. And we can, let's say, test detector hardness, I mean radiation hardness, by applying later on heavier ions. Then this current rate can really change a lot. We can quite well control which current we want to put on our detector by opening and closing the slits, or on our sample in general. We have good definition of position, and we also can do some 2D imaging. So we can really relate position of the ion and place at the sample. We can use test different ranges of detector from let's say 1 to 500 microns by changing the ion type and energy. And also the position of the energy in our system will vary from, let's say, 10 to 1,000 keV per micron. So we can really deposit different amounts of energy in our detector. So this is also nice to see. Let's say if you look that your target is silicon, let's say silicon diode, and you start with lightest ion, let's say with hydrogen or protons having energy 1 MeV, you can probe 16 micron depth in silicon. But if you increase the energy of your protons to 10 MeV, you will see much deeper, and you will be able to probe something like 700 microns. But if you use, let's say, very heavy ions, like iodine, with 1 MeV iodine, you will probe only 317 nanometers. But if you use 10 MeV iodine, you will probe more, but this will be in microns. So you see that at 10 MeV iodine, it will stop earlier than 1 MeV proton, much earlier. Or 10 MeV iodine is having a similar range like 1 MeV alpha particles in sample. So this is really then a versatile tool to design your experiment and to do exactly what you want on depth where you want. Also, it's nice to compare how protons look if you want to compare them, how the path looks in the sample, comparing to heavy ions and to electrons. So if we have electrons, they will immediately after they enter the sample, they will spread because of many scattering electrons on electrons in your sample. But if you look 2 MeV protons, they will really go straight and deep, and they will have some small distribution, but this aspect ratio is really good for doing some, let's say, micromachining or some defect engineering and so on. This is completely different than very light ions, very low energy ions, excuse me. Let's say 50 keV heavy ions. they will stop very fast and they will do a lot of damage, because when ions have low energy, they interact with the material mainly through nuclear stopping. And high energy ions, they interact with material mainly through electronic stopping, and at the end of the range, they do damage. Actually, they interact with the material by making vacancies and displacements and damage. So this is a beautiful thing because you can use it also for modifying your materials. So let's go back to the ion beam induced charge, and very simple case. So we just look the standard silicon pin diode, which is having a charge efficiency 100. So first, if you do IBIC, you will have only this red region everywhere. And then you can do damage of this diode with different ions in different shapes, as you can see. And then you probe it again with the IBIC. And you can then see where you have produced the damage and what is the height of your signal after damaging material. So you can see how your detector is degrading with the fluence of ions you put inside. For instance, here you have two different square regions, and you put here, let's say, 6 lithium-7 ions per square micron, and here you put 50 lithium ions per square micron, and you see that this signal is higher, orange, than this, which is yellow-green. So you made more damage in your material if you put more ions to some place, which is quite understandable. This is one very nice example, which was done by my colleague in our laboratory. So my colleague is doing PhD by studying charge collection efficiency of these single crystal CVD diamond detectors, but not at room, then on low temperatures, because this is also important for some applications. So what he did, he put this CVD diamond detector here in the special cell, which was cooled down to different temperatures, down to 47 kelvins. So he can control the temperature with some cold finger and some electronics. He can check what is the temperature. And what he has established, that by using different ions and going down with the temperature, you can reduce the charge collection efficiency of your detector, meaning your detector will not work so well as on high temperature or normal temperature, because you expect that normal working detector is having a charge collection efficiency around 100%. So by lowering down the temperature and using different ions, you can see that this also depends on ion, and that it will not decrease equally for every ion, but will be drastically reduced for 100% to 40 and 30%. So let us go now to materials modification using ion beams. So when we talk about materials modification, there is really a lot of things that can go on. So well known to all of you, and technique which is used since 60s years of the last century is ion implantation. When you actually inject the foreign ions and they stop in the material, but you can also inject the same ions, same species as this material, to study damage. This is let's say, very important for fusion research. You can have heavy ions. We said the heavier the ion, the energy loss per unit length is higher. And just by passing some ions, can make some damage into the material, which will completely change this material. We can then form some tracks or some nanopores. I will talk a little bit later about. And this material is completely changed. Or we can have this irradiation with protons. This is used for lithography and also for defect engineering. I will also give some example later. So ion implantation today is used not only for doping of semiconductor materials. So we put some ions which stay in the material. We sometimes do some annealing or some other procedure. And this can be very useful for improving, except doping, for improving hardness of different tools. That is, for instance, doping of nitrogen in steel. Also, we can improve resistance, wear friction of prosthetic devices. And we can do some mixing of ions and some interface to change this interface. One of the tools which is also used and can be used in the framework of remade ARI project is helium ion microscope. So helium ion microscope uses low energy helium ions. So this is ions in the range of 10 to 35 keV, and they have very good lateral resolution. They can be focused to dimensions better than nanometer. So let's say 0.5 nanometers. And this can be used then for defect engineering, implantation, imaging, nanofabrication of conductive and isolating materials. Here I just have two simple, nothing is simple, but two examples. One is defect engineering in case of single layer 2D material. So you can see that by helium ions, you can engineer some defects. Or here it's also point irradiations with helium, which introduced some protrusions on the surface on this side of the diamond microscale disc. So really you can do it really precise, and you can really create different nanostructures. Also, it's important to mention something about focused ion beams, which are used also can be used also to do some defect engineering. Focused ion beams also have a diameter in the range of few nanometers. Let's say here you can see one example I found in the literature that is implantation of 35 keV silicon into silicon carbide. And that is maskless. You don't need to do mask. You can really put these ions in the positions which you want, which are with a 5 to 10 nanometer precision. And you can repeat it many times, so you can put many ions. So the response to emitting light, to emit light depends on the number of silicon ions you put on one place. So you can get more higher light signal, and that's important. Also, these applications are important for quantum technology. This is one example from my lab. So this is also some attempt to do single ion implantation, but this time this was for creating NV centers in diamond membrane. So this is implantation of nitrogen ions with the fluences with the energy of 700 keV, and fluences in this upper case, the fluence is 10 to the 10th ions per square centimeter. So you again see this light emitting there is a lot of with this fluence, a lot of these NV centers are created, and they are overlap also. But if you reduce the fluence of ions 1 order of magnitude with the same energy of nitrogen ions, you will make more better separated and single NV centers. So this is not ordered, but this can be also done by using ion microprobe, for instance, and some trigger which will tell you when you placed one ion to move on another place and that equidistant. Here is also one example of this ion beam assisted ordering. So you also need for quantum applications some quantum formation of quantum dots in semiconductor materials. And this property of these quantum dots are closely related to the size and shape of individual dots. So those quantum dots are basic building blocks of future nano devices. So here we have some sandwich made of germanium and SiO2 that was done by magnetron sputtering. You see that this is a very nice homogeneous multilayer. Then you irradiate this multilayer with 3 MeV ions. And if you look closer, you can see that you have some density modulation. This is not any longer so homogeneous layers as after deposition. After some annealing at 800 degrees, you can see that you have formed nanodots and that these quantum dots are following the irradiation direction. So you can, by tuning the irradiation angle and the fluence of the ions you put on this such a material, you can tune the size of the quantum dots. This is a one also very nice example, which was done in collaboration with colleagues from University of Torino in our lab. So, you know, the diamond is a very nice material and it's also used for detectors. But in this case, what they wanted to produce is to produce deep in diamond. In this case, on some depth, I don't know, this is maybe couple of microns, to turn diamond to graphite. So this graphite deep inside the diamond can be used then as a conductive channel, because you know that graphite is completely different than diamond and is conductive and etchable. So you can produce such a devices for biosensing of single cells. So you can put single cell on this and look at the response of the cell. You can make this beautiful conductive channels inside. And you can also use it for microfluidics, because graphite can be etched out, and then you have this empty space which can be then filled by fluid or something. Heavy ions, which lose a lot of energy per unit length, can make permanent damage, and after some etching, you can have ordered these ion tracks. So you have something like these nanopores, which you can put track membranes, and you can, for instance, put some material inside them and then melt them completely, and then you can produce some nanowires in materials. This is also one example done in our lab, where we were looking at this surface. What is the stopping needed to produce visible ion tracks at the surface of this strontium titan oxide? And we found the threshold needed for production, and that this threshold is around 12.5 keV per nanometer, which is then something like 23 MeV iodine ions. They produce enough, they deposit enough energy to make permanent ion tracks on the surface of material. So basically you can, with ions, you can modify surface and you can make some patterns on the surface at the surface and produce different shapes. So one of the techniques also that is used is ion beam lithography. So when you irradiate with high fluences protons, let's say some PMMA, these plastic materials, you can break chemical bonds, and this after etching, all this material will be removed. So you can get some structure like this. You have also, these are positive, and you have also negative resist that, let's say, etching of SO8. When you irradiate this material with 2 MeV protons, you can etch those parts which are not irradiated. So again, you can get some template where you can grow some structures or produce some devices on material. And the advantage of ion beam lithography is, again, that you have this high aspect ratio. You see here on this beautiful micron size stone hedge, which was done by the group in Oxford long time ago, but it's really beautiful and is demonstrating several things. One of these things is that you have really nice range, and that at the end of the range of the ion, you have this broadening. Other thing is that you can tune with energy and probe different depth in material. So here they used lower energy ions, here they used higher energy ions, and to produce such a structure. So ion beam lithography is used for many applications like lenses, waveguides, biochips. You can make some structures in porous silicon and so on. So this is all I prepared. I hope I have convinced you that you have nice ion beam analysis techniques that can be used alone or in combination to get information about the composition of your sample. You can use broad beam, you can use focused ions to get lateral distribution of elements or isotopes. Techniques are quantitative, we like to say non-destructive, although this is not completely true, but it's true in most cases. Relatively fast, we can determine all range of element from hydrogen up, and we can give information about elemental depth profiles. And with ion beam modification, this is really broad range. So from keV ions to GeV ions, I didn't talk about GeV ions because in radiate, I think there is no facility offering this, but MeV ions. So you can really tune ion type, tune energy to probe your different depth in the sample, to introduce defects, to implant some species, to make tracks, to make some structures with lithography and so on. And thank you for your attention.
Thank you very much, Iva. Very interesting information on this technique. Are there any questions from the participants? If there are, please type them in the Q&A region, and I will then address them to Iva. And also, in a few minutes, Valerie will kindly add a link for a survey to give us some feedback about these webinars. Waiting for a couple of minutes in case there are some questions. Can I ask you, Iva, this idea about the ion implantation sounds very interesting. So if I understand correctly, it depends on the energy of your ion beam,
Yes.
the effect, but is there a limit on how deeply you can affect your sample?
Yeah. This depends on the ion type, and more energetic ions and lighter ions will go deeper in the material, and so you really can tune with your energy and a type of ion what you want to probe. Also, the fluence is very important, because after some fluence, materials will be permanently damaged. So sometimes you want to introduce this damage or these things, but sometimes you want to avoid them. So you have to be very careful to know what you want to do, which fluences to use. Everything depends on the experiment. So if you know what you want to achieve, then it's easier to design the experiment to see which setup will be perfect for your experiment and what you want to achieve. So you can really tailor it with the needs of the user.
Right.